If you're writing anything, literally anything, even remotely similar to the answer we're about to look at in your Cambridge 0625 physics exam, you are actively throwing away your grade. Let's fix that right now.
Okay, let's dive right into this bleeding paragraph. Energy is made by the battery and used up by the motor. Now, this is an incredibly common answer on energy conservation, and honestly, it looks absolutely fine to a novice. I mean, it makes logical sense in everyday conversation, right? But the second the examiner sees this, they are going to strike it with a giant red zero. Why? Because in physics, saying energy is made or used up completely violates the fundamental laws of the universe. It shows a total lack of understanding of energy stores and transfers, and it instantly signals to the examiner that you just don't know the core syllabus terminology.
And guys, this is exactly why ordinary revision fails. You can spend hours highlighting your textbook, memorizing all the different types of energy, and nodding along to explainers all day long. But here's the reality. You aren't just tested on the existence of facts. You lose marks to specific, fatal flaws in the exam hall. I'm talking about missing units, like writing 50 instead of 50 joules. I'm talking about rounding way too early in a multi-step calculation which cascades into a completely wrong final answer. It's the vague explanations, substituting the wrong variables into your equations, or offering hopelessly weak practical improvements. These right here, these are the exam killers.
So what's the fix? The absolutely crucial point is applying a strict, four-step surgical framework to cure those mistakes and guarantee top-band marks every single time you face an energy question. Step 1, you identify the core concept. Step 2, you pull the exact evidence or data straight from the question prompt. Step 3, provide the scientific reasoning that links that data to the concept. And Step 4, honestly the most important one, wrap it all up in the exact examiner wording they are desperate to see on the mark scheme.
Let's look at Step 1. Step 1 is nailing the concept using exact terminology, because defining this law perfectly is your primary weapon for securing that first mark. The principle of conservation of energy states, energy cannot be created or destroyed, only transferred between stores. You need to memorize this word for word. Energy doesn't just disappear. It doesn't get used up. It simply shifts from a chemical store in a battery to an electrical pathway to the kinetic store of a motor. And invariably, some of it is wasted as a transfer to the thermal store of the surroundings.
And this brilliantly illustrates the fix. Watch how we take that vague, broken answer from earlier and replace it with our structured, examiner-safe framework. Instead of saying energy is made, we state the concept. Energy cannot be created or destroyed, only transferred. Then we bring in the data. The 100 joules of chemical energy input equals the 60 joules of useful kinetic output plus the 40 joules of wasted thermal output. Finally, the reasoning. This proves conservation, though the efficiency is less than 100% due to thermal dissipation. Boom, you've just turned a zero-mark disaster into a perfectly structured full-mark response.
But let's escalate the stakes here. Describing energy transfers is really only phase 1. Cambridge will inevitably force you to prove your understanding by calculating it. They'll take these abstract energy stores and demand that you quantify them using work and power equations. And honestly, this is where the math anxiety kicks in for a lot of students, causing them to drop easy method marks.
In a moment, I'll show you the examiner clue that changes the calculation completely, but first, you need the framework that makes that clue obvious. You see, you cannot decode the exam paper if you don't actually understand the mechanical bridge between forces and energy. Let's build that foundation right now. Work done is simply energy transferred. Seriously, that is the golden rule. When a force moves an object through a distance, energy is being transferred from one store to another. The equation is work equals force times distance, or W equals F times D. Now, force must be in newtons, distance must be in meters, and the resulting work done is measured in joules. So if you push a box with 50 newtons of force over a distance of 2 meters, you have done 100 joules of work. You have mechanically transferred 100 joules of energy to that box's kinetic or gravitational store. Now, what's really interesting here is how power introduces time as the critical new variable you must isolate in your data. Power is the rate at which work is done or the rate at which energy is transferred. Power equals work done divided by time taken. P equals W over T. The unit here is the watt, which is exactly equivalent to 1 joule per second. Think about it. If two motors do 100 joules of work, but motor A does it in 2 seconds and motor B does it in 10 seconds, motor A is significantly more powerful. It transfers 50 joules every single second, while motor B only transfers 10. You must always comb the exam question for that time variable and make absolutely sure that it is in seconds, not minutes or hours, before you substitute it into your formula. Okay, let's test this under pressure. I want you to pause and predict. Look closely at the steps for the sufficiency calculation.
The student has a total energy input of 1200 joules and a useful energy output of 400 joules. They write down efficiency equals useful energy output divided by total energy input. They substitute 400 divided by 1200. They calculate 0.33, and their final answer line says 0.33%. What massive, mark-destroying error has the student made here?
It's devastatingly simple. They completely forgot to multiply by 100 to convert their decimal into a percentage. 0.33 as a decimal is 33%, but by writing 0.33 with a percentage sign next to it, they are literally claiming the machine is 0.33% efficient. The examiner is going to penalize this immediately. You must either leave it as a pure decimal ratio of 0.33 or explicitly multiply by 100 to state 33%. Do not mix them up or it'll cost you the final accuracy mark.
Let's break down this data table because mixing up useful output with total input is a classic example of falling into the wrong variables trap. Imagine a standard light bulb. You plug it into the wall, that electrical energy is your total energy input. The bulb produces light, which is your useful energy output, but it also produces heat, which is wasted energy. The trap happens when a question gives you the wasted energy and the total input and asks for efficiency. Students will panic, divide the wasted heat by the total input, and get the exact inverse of the correct answer. Always, always identify which energy store is actually useful for the intended purpose of the device before you even touch your calculator.
Another massive trap is rounding too early. If you calculate an intermediate value of 0.33333 recurring, keep it in your calculator. If you round an intermediate value to 0.33 in part A of a question, and then use that rounded number in part B to find total power, your final answer drifts further and further away from the mark scheme. Always use exact values during those intermediate steps, and only round to 2 or 3 significant figures at the very final answer line.
Right, let's jump into a data analysis challenge. When you're confronted with an energy transfer graph, maybe it's showing the cooling curve of a material or the power output of a solar panel over time, what is the absolute first thing you must verify before you even try to calculate a gradient or the area under the line?
You must run this diagnostic check immediately. Check the axes labels. Verify the units. I guarantee you, at some point, Cambridge will try to trick you by putting time in milliseconds on the x-axis or energy in kilojoules on the y-axis. If you calculate a gradient using 5 instead of 5,000 because you missed the kilo prefix, you lose the marks. No exceptions. You also need to ensure that any conclusions you write are explicitly supported by the data shown. Do not extrapolate wildly beyond the graph unless the question specifically asks you to estimate.
Okay, here is the clue I promised earlier. Command word fulfillment. The very first word of the question dictates exactly which part of our 4-step framework gets the most weight. If the word is state, they just want the concept. If it's calculate, they want the data, substitution, and units. But if it says explain or evaluate, you need the full framework. You need the scientific reasoning linking the physics concept to the specific data provided. If you just describe a trend when you're asked to explain it, you will cap your marks at half. It's as simple as that.
Let's apply this clue to a practical investigation question. When designing an experiment to measure power or energy transfer, you are essentially building out specific steps required to harvest every single method mark available. Step 1. Identify the exact apparatus. Don't just say use a meter, say use a voltmeter placed in parallel. Step 2. Note exactly what values you are recording, like the initial temperature and the final temperature. Step 3. Explicitly state the equation you will use to substitute those values into. This proves to the examiner you know exactly how the raw data turns into a final energy value.
Time for the ultimate exam challenge. In a practical question about thermal energy transfer, say, measuring the specific heat capacity of a metal block, where do students bleed the most marks when they are asked to improve the reliability of the experiment?
The examiner's style correction here is absolutely brutal. Writing vague, weak practical improvements like be more careful, read it better, or use a better thermometer will score you absolutely 0 marks. You must identify specific apparatus features to upgrade based on the physics. A top-band answer says something like, add lagging or insulation around the metal block to reduce thermal energy transfer to the surroundings, or read the thermometer at eye level to avoid parallax error. You must be highly specific about the physical mechanism causing the error.
So before you rush off to the next page of the exam, always run your final answer checks. Are the units present and correct? Joules for energy, watts for power, dimensionless for efficiency. Are your significant figures correct? In Cambridge 0625, you should generally give answers to 2 or 3 significant figures. Is your graph scale reasonable, covering at least half the page? Did you note any safety precautions if the experiment involves high heat or high voltage? These final mental checks are literally the difference between an A and an A star.
Now, we've fixed the calculations, we've fixed the terminology, and we've nailed the methodology. But that leaves a massive unresolved problem. What happens when your calculated practical data completely contradicts your expected energy conservation model? I mean, what do you do when your total input does not mathematically equal your useful output plus your identified wasted output, and you're left with missing energy?
When you are staring at contradictory data in the exam hall, panic is not an option. You must trust your core principles. Acknowledge the missing energy and critically evaluate the physical environment to identify the unmeasured thermal transfers that your initial model missed. Energy doesn't just vanish, it escapes through pathways you simply haven't accounted for. Understanding how to structure this exact evaluation is absolutely critical for your final grade, which brings us to your mandatory post-surgery rehab. For the exact strategy to map out the rest of your revision, you must subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations.
Fixing your basic calculations is only step one. Recognizing the messy reality of physics is where true mastery begins. Because in the real world, energy conservation doesn't happen in a perfect vacuum. So when your theoretical calculations don't perfectly match your real-world data, you need to know exactly how to answer. Don't leave your grade to chance. Click the video on your screen right now for your Physics 0625 Last 7 Days Revision Map. It is the mandatory next step to ensure you don't drop a single mark. I'll see you over there.